Hey everyone. In the last video, we talked about some of the key kinematics definitions, things like velocity being the rate of change of position with respect to time, acceleration being the rate of change of velocity with respect to time, and from these definitions, we were able to identify key equations like average velocity is change in position over change in time. Average acceleration is change in velocity over change in time. We talked about how the change in any quantity, whenever I have delta something, that's always going to be final minus initial. And we also talked about how the position, velocity, and acceleration are related to each other graphically. So, for example, velocity is the slope of a position versus time graph. Acceleration is the slope of a velocity versus time graph, and how we can relate these quantities using calculus, so using derivatives and integrals to change between different kinds of quantities. What I want to do in this video is look at a particular set of examples where we have a constant acceleration system. That is where both the magnitude and direction of the acceleration remain constant the entire time. So if we have one of these constant acceleration systems, we can use some of these earlier properties, either using calculus or using some of the graphs of the motion, to actually derive a set of equations that will describe how different aspects of the motion will change, again, under this assumption of a constant acceleration. So the terms in here, the x's, again, all represent positions. X on its own is just final position. Whenever we have one of these subscript zeros, it just means the initial value at time t equals 0. So this would be initial position. We've got final velocity, initial velocity, we've got acceleration, and time, all being related in these sets of equations. Now, if you look up constant acceleration equations, you're going to see lists that sometimes contain more equations than what we have right here. I do find that these three equations are the ones that are most often used. And those other versions of the constant acceleration equations, you can actually derive them from this set of equations. In fact, the third equation you can actually derive from the first two on their own. We're not going to derive these here themselves, but let's see if we can have a look at some actual constant acceleration systems and compare the motions that we actually observe with some of these equations. So let's have a look at that. We've got our low friction track. I've got my motion sensor, which is going to be tracking the motion of this cart, and I've set up the coordinate system for this motion sensor. So approximately here is where position 0 is going to be, and to the right is the positive direction. And since this track is leveled, if I give this a bit of a push and start taking a bit of data, then we should get an approximately constant velocity. Let's scale all these graphs. Our velocity is staying pretty much constant. Our acceleration is basically hovering around 0. And our position versus time graph should be a straight line, a constant slope. And as we mentioned in the last video, the slope of that position versus time graph, well, the slope of this position versus time graph is giving 0.347, which matches up with our velocity data very nicely. The slope of a position versus time graph gives velocity. Now, I can make this system have an acceleration by putting some risers under each end of the track. So if I put risers under this end of the track, that means we're going to have a positive acceleration. This cart is going to be trying to accelerate down the length of the track. And let's see what we get when we start out some of this motion. So let's reset the motion sensor, and here we go. Definitely going to have to auto scale all those. And in this motion, notice we're getting approximately a constant acceleration for most of the motion once I had let go of the thing. And let's compare these graphs with what we got for our constant acceleration equations. So if we have this constant acceleration, this velocity versus time graph should be linear with time. Again, this is final velocity equals initial velocity plus acceleration times time, should be linear, and the slope of that velocity versus time graph should give us our acceleration. So the slope of this velocity versus time graph gives 0.637 meters per second squared. if I highlight the same section of data, let's make sure that's approximately the same section of data, so I'm highlighting, again, this section of data, and I look at the statistics for that acceleration data, cool, 0.639 meters per second squared, very close to our 0.637 meters per second squared. And also notice that our position data forms a very nice parabola. In fact, if I do a quadratic fit to this, notice that quadratic fit matches very, very nicely with our data. The position graph, the position versus time graph, is quadratic in time. We have this time squared term on there. So that matches up with what we were describing before. Also, we have this positive acceleration, and we said the position versus time graph should have an upwards curve to it. Again, that matches what we see. Let's switch the risers and look at what happens when we have a negative acceleration. So if I put the risers on this side, now the cart is going to be trying to accelerate in the negative direction, and let's see what we get when we run through some of this data. Okay, looks good. So if we auto-scale all these graphs, then notice we've got a fairly constant acceleration. Our velocity versus time graph, if we highlight that velocity versus time graph, the slope, the downward slope of that velocity versus time graph pretty closely matches our acceleration. If we look at the same set of data, then that's the slope of that velocity versus time graph very closely matches the average of our acceleration versus time graph. So again, in the case of this constant negative acceleration, our velocity graph is still linear, and our position graph is quadratic, but this time it has a downwards curve to it. If I compare that with a quadratic fit, well, those match up very, very nicely with each other. So this data supports the fact that we have these constant acceleration equations, the velocity graph should be linear with time, and the position graph should be quadratic with time. So those patterns look great, but let's see if we can use these constant acceleration equations to make quantifiable predictions about how an object will move under certain circumstances. So consider the following case. An object is going to start at the top of a ramp of length L, start from rest, and then slide to the bottom in a certain amount of time. We're going to actually set that up and measure the length of the ramp and the time it takes to reach the bottom of the ramp. And then we're going to use these constant acceleration equations to calculate what is the acceleration of the object and what is the velocity just as it reaches the end of the ramp. And we're going to see if these constant acceleration equations can match those particular measurements. So again, the position 0 is right about here for the cart, so I'm going to hold that in place. We're going to start the sensor and then again release this thing from rest and see how it moves in this particular case. So let's give it a shot. Okay, data looks pretty good. So what we need to do in this case is again identify what is the length of the ramp and how long did it take to actually reach the bottom of that ramp. So if we look at these two graphs, we can say the object was just starting to move right around 0.24 seconds, and the time when it reached its maximum velocity, again, this was just as it started hitting the end of the ramp. It still moved a little bit further forward as the spring compressed a little bit, but just as it reaches the end of the ramp, the time is 1.64 seconds, and our position on the ramp is 0.802 meters. So the length of the ramp was 0.802 meters. And again, the time that it was falling for, we said it started from 0.24 seconds and ended at 1.64 seconds. So that would be 1.40 seconds for the time it takes this thing to go down the ramp. And let's actually go through the calculations for how to use these constant acceleration equations to predict the acceleration and the final velocity of this object, and then check it against these actual results. So now that we've got the length of a ramp and the time of the slide, let's start working the problem, and I always recommend starting with a diagram. So we've got the ramp that we were using, we've got the cart at the top of the ramp, the cart when it gets to the bottom of the ramp, and we want to label on this diagram some relevant quantities. We're defining our coordinate system such that we're starting from position 0 meters. We're calling down the ramp the positive direction, and at the bottom of the ramp, that distance is 0.802 meters. We also know that we're starting with an initial velocity of 0. We are starting from rest. Sometimes terms that are written into the questions imply certain physical quantities. And we're trying to find out how fast this thing is moving at the bottom of the ramp, so the final velocity. We also want to find the acceleration, but our time is 1.40 seconds. Now, let me start with a way of attempting this question that is incorrect. I see a lot of students make this mistake, so I just kind of want to highlight how this mistake is made and how to avoid it. So a lot of students see, oh, I've got a time, an initial position, and a final position, so let's use this equation to get a velocity. So we'll get that velocity is our change in position over the change in time. We'll get a value for that. And then now that I have that velocity, let's find the acceleration by using this average acceleration equation. So they'll use acceleration is change in velocity over the change in time. And the students will just use this equation and plug that in for our change in velocity. But we have to be very, very careful. Each of these different velocity terms talk about different things. We've got initial velocity, we've got final velocity. This quantity here, this is the average velocity. It's not the starting velocity, it's not the ending velocity, and it's also not the change in velocity. All of these terms are referring to different physical quantities, so we want to make sure we don't get them mixed up with each other. This is part of the reason why drawing a diagram and specifically listing out those quantities, highlighting when are we talking about average velocity, when are we talking about initial or final velocity or a change in velocity, you have to be very, very careful in which of those quantities you're specifically trying to measure. So what's the better method of finding this value? Well, in this particular case, notice we have initial position, final position, we've got initial velocity, we've got time, and we want to find the acceleration. So we want to identify which of these constant acceleration equations involves the thing that we're trying to solve for, and the only other quantities are things that we know. We don't want to have any unknowns. In this case, our final velocity currently is unknown. So let's avoid the equations that involve final velocity. And in this case, let's go with the second equation. So that second equation is final position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. Okay. Again, notice that this equation involves what we're trying to solve for, the acceleration, and all of the other quantities are known. I know the final position, initial velocity, and the time. So let's sub in some of those quantities. So our final position was 0.802 meters. Our initial position was just 0 meters. Our initial velocity was 0, so that whole middle term just goes away. And we've got 1/2. We don't know what the acceleration is yet, but we know that the time is 1.40 seconds, and that has to be squared. Make sure you also don't forget to square values. It's really easy when going from one line to another to drop terms that are squared, things like that, for instance. Okay. So we can rearrange this equation. We can multiply both sides by 2. So let's multiply both sides by 2. You know, this 0 term here doesn't really matter. And then we're going to divide both sides by 1.4 squared. And when we evaluate that, we get our value for acceleration being 0.818, and that would be in meters per second squared. We're dividing by 1.4 seconds squared. So let me include those units. And we get that acceleration, again, in meters per second squared. Well, let's check that against our actual data. So here is our graphs, and we can actually add a graph for acceleration and quickly scale those. And for this motion, if we look at the accelerated motion and look at the statistics for that, looks like our value for acceleration is, the average value for that acceleration data is 0.817 meters per second squared. We got 0.818 meters per second squared. Very, very close agreement between those two values. So that looks great. Next, we want to figure out what is the velocity when it reaches the end of the ramp, this final velocity. Well, now that we know the acceleration, let's try using equation 1, saying I want to find the final velocity. I know the initial velocity is 0. I know the acceleration and time. So let's use equation 1. And subbing in our values, the initial velocity was 0 meters per second. Our acceleration, we just calculated, that was 0.818 meters per second squared. And the time that it was going down the ramp for was 1.40 seconds. And if we multiply those together, I get 1.145 meters per second. And again, let's check that against our data. So if we look at the velocity graph and find what was the velocity at the just before it hit the end of the ramp, we get 1.19 meters per second. And compare that 1.19 with 1.1445, we get some pretty good agreement for that as well. Another way that we could have had a look at this is, let's also try this using equation number 3, because we haven't used that equation yet. So let's say that we had a situation where we knew the initial velocity, the final velocity, the distance along the ramp, and we wanted to solve for the acceleration using that data instead. Well, in that case, we can look at equation 3. So we've got v squared, so the final velocity squared, is equal to the initial velocity squared, plus 2 times the acceleration times my change in position. And for this final velocity, let's use the one that we calculated just to make sure things are self-consistent between this particular set of equations. So we could sub into here 1.145 squared equals our initial velocity squared. Well, we don't have any initial velocity, so we can just get rid of that term. And we have 2 times the acceleration times that change in position. So final position minus initial position, that's going to be 0.802 meters. And, well, if we do 1.145 squared, and then divide both sides by 2, and then divide both sides by 0.802. So divide by 2, and then divide by 0.802. The acceleration that I measure from this is 0.817 meters per second squared. Again, within rounding of what we had for the previous measurement. These 3 equations for a constant acceleration system are both self-consistent with each other and consistent with measured data. One very common type of constant acceleration motion is the case of projectile motion. So if I have an object that is only under the influence of gravity near the Earth's surface, so not being affected by air resistance or any lift forces or anything else, then the acceleration of that object will be pointing straight downwards towards the center of the Earth, and the acceleration's magnitude will be 9.8 meters per second squared. We call this value little g, and I will link a video where I actually measure this value of g with an experiment. And this has some interesting consequences. If this acceleration is straight downwards, then there is no horizontal acceleration, which means my velocity in the horizontal direction won't change as the particle is going through that motion. Again, we are assuming that there's no air resistance or any other forces acting on this object. And in the vertical direction, well, we start with this velocity going upwards. As time goes on, that upwards velocity is going to get smaller and smaller, reach 0 near the top of the motion, and then our velocity is going to be pointing downwards. And as we fall, that object's going to be speeding up. This actually matches with some other properties that we talked about, saying, let's say I have an object where the velocity is going in this direction and the acceleration is going straight down. In this case, the motion of that object, it's going to be slowing down and the path of that motion is going to be curving. So slowing and curve. And then after it reaches the peak of the motion, now we've got this object. It's now moving in this direction, and the acceleration is still pointing straight down. So on the other side of that motion, when it's starting to fall back downwards, now this thing is going to be speeding up and still turning on that kind of parabolic trajectory. So let's look at a particular case of analyzing this motion. We're just going to look at the one-dimensional case, but for two-dimensional motion, we'll probably talk about that in a future video. And for two-dimensional motion, you can basically just break up what's happening in the horizontal direction and go through these equations just looking in the horizontal direction, and separately say what is happening in the vertical motion. So just look at this with the vertical components of motion. But let's look at this particular case. We've got an object dropped from the top of a 3-story building around 11 meters above the ground. How long will it take to reach the ground, and how fast will it be moving just before it hits the ground? Again, good starting point. Let's draw a diagram. So we've got this building. Let's call the ground height 0, and we are dropping it from an initial height of 11 meters. So our initial position is 11 meters. Our final position is 0 meters just before it hits the ground. When it hits the ground, it's no longer a projectile. So when we're discussing things like projectile motion, and we're saying I'm dropping or throwing or shooting an object, something like that, we're looking from the moment that it leaves my hand, or the moment that after the object is shot, to the moment before I catch it, or it lands, or it hits the ground, or something like that. So we start out with a position of 11 meters. Our final position is 0, just before it hits the ground. We don't know how fast it's moving just before it hits the ground. But we do know that if I'm dropping the object rather than throwing the object, if I'm just releasing it, at that first moment that I release, the velocity will be 0. So our initial velocity is 0. And since this is a projectile, when I let this thing go, that acceleration in this vertical direction will be negative 9.8 meters per second squared. And again, we want to find out what the time is, how long it's going to take to reach the ground, and how fast it's going to be moving just before hitting the ground. So let's try to solve for that time first. Well, we know initial position, we know final position, we know initial velocity, we know acceleration, and we're trying to find time. So let's look at equation number 2. So we said our final position is 0, our initial position is 11 meters, our initial velocity is, again, 0, so this whole term goes away, and our acceleration is the acceleration due to gravity of negative 9.8 meters per second squared, and we want to solve for the time. Well, we can combine some things together. We can subtract the 11 meters from both sides. We can do 1/2 times negative 9.8 is going to be negative 4.9 meters over second squared times time squared. And then let's divide both sides by this negative 4.9 meters per second squared. And that gives me time squared is equal to 2.24 seconds squared. And then we have to take a square root of both sides. So take a square root of both sides, and I get the time for this thing to hit the ground is going to be basically 50 seconds, just shy of 1.5 seconds. And again, this is something that makes a testable prediction. You could drop an object, make sure no one's below you if you're dropping objects off of buildings. You can drop an object and time how long that takes to happen. Well, what about how fast it's moving just before it hits the ground? Well, now that we know the time and we want to find the final velocity, let's go back to equation 1. So for equation 1, we've got our final velocity is initial velocity plus acceleration times time. Initial velocity was just 0, so that goes away. Acceleration is negative 9.8 meters per second squared. And our time was 1.50 seconds. And if we multiply those together, we get negative 14.7 meters per second. Where did that negative value come from? Well, that negative, remember, velocity is a vector. Direction matters. So that negative sign comes from the fact that this object is moving downwards just before it's hitting the ground. Okay? That negative sign accounts for that direction. So we've gone through a few of these constant acceleration examples, and I've posted a few more examples for you to try on your own, maybe using the first two constant acceleration equations to derive the third one, see if you can try that one, and a few more examples of projectile motion and motion not on the Earth. If we had a different value of g, how would we calculate that? So give those a try. The solutions will be posted in the description. As always, if there are comments or questions about any of these methods, feel free to throw those into the comments, and see you in the next video.